Hello, everyone. Welcome to this week's discussion section. We're almost done. Yeah. So in this discussion section, we'll be talking about more design-oriented questions. No, like in the past lectures, we have been seeing about data path controller separation, no? To make our design more simple and not have to deal with these enormous truth tables. So we're going to now do some exercises related with that. Yeah, let's just get started. So we have this question that is basically telling us to implement that pseudocode using a circuit. No? I guess traditionally you would have to again take the truth table of everything here and have this giant table with a lot of logic gates, but again, based on what we have seen, we can simplify that by using a more abstract view of the problem we have here. But let's just read the problem statement here. So the following is the pseudocode for an algorithm that using Newton's method for calculating square root, and the input is x, no? Output is y, and both are floating point numbers. Here we don't really care about if there are integer point numbers, or floating point numbers, we will just don't care about that. Let's assume we have a circuit that has the elements necessary to compute in whatever representation they are. And the computation is triggered with a signal go for one cycle that loads the input to a register that holds x. The computation completes by asserting a signal done for one cycle. So they're telling us to implement this code as a controller and data path. And the first step to do this is draw a flowchart of this algorithm. If you have ever been in, I guess, computer algorithm design course or whatever, you know that there's this first step. When you have a problem, you first design its flowchart, and maybe then you do the pseudocode. Here they're already giving us the pseudocode, but we still need to a good way to understand which states do we have to implement in our controller, and how also which stages to implement in our data path is to draw the flowchart. So they're also telling us to write the finite state machine diagram and build the data path, no? Using the building blocks that are available below. So they're telling us that we can use multiplexers as much as we want, registers, one magic adder. It's magic because we don't care really its implementation. It just adds to floating point numbers. But we can just right now think of them in a more abstract way. We don't need to delve into what's behind these adders. That can add either floating point or integer, and one magic divider. So we have one adder and one divider, as many multiplexes as we want, and as many flip-flops as we want, no registers. So why is the iterated solution to algorithm? Just a few states as possible. Yeah, no. So let's just check what is in fact being done here. Also, it's initially y is equal to 1, I is equal to 0, and while I is lower than 128. In fact, we don't need to check at first this condition because I is initialized to 0, but whatever. You say this is equal to 1/2. Right. Now this is what we are doing here, and then it's adding 1. We can transform this into plus. Then if we pass this to the other side, it will be 1y equal to xy. And if we pass this to here, oh no, wait, I'm missing something. Oh yeah, this, no? And then if I pass this to here, this will be, and then, so yeah, you can see that this doing this square root operation, but only through many iterations to approximate the correct value, no? But yeah. But yeah, I guess before we start, I just wanted to tell you one way of representing variables. Let's see. So usually, how do you represent the variable? Well, with a flip-flop, no? You can say a flip-flop maintains the state of whatever you have there, but you can also use it to represent any value, any variable in this case. We have two variables, y and I, and we have an input that is x, that we may also want to maintain its value, but let's assume just with y and I, for example. So ideally, we would have this, no? A flip-flop, maybe let's call it a D flip-flop. And this is y, no? And as you can see here, y is initialized with 1. So this will be, but as you can see, how can we update the value of y? Like you can see, yeah, y is initialized with 1. Well, how can we now then put this value? Should we put another flip-flop, or what should you do in order for changing this value of y, but also be able to initialize it with a 1? Do you think we should add something here? Do you think we should have two flip-flops? No, maybe something like this to I don't know. What do you think we should do in order to allow for this case where we first want to initialize y with 1 value, but then we would like to this flip-flop to be updated with a computation or something, no? For example, maybe adding I don't know, value x to this, no? And then we want to, for example, we want to do this operation. First is y equal to 1, but then it's y equals to y plus x, which is this. But how would you then update this y value? Any thought on that? How would you make this flip-flop serve in these situations where you want values from different parts to affect the y at different moments? How would you control it, I guess? Using some of the modules you have seen in the past. At some points we want to initialize with 1. At other points we want to do this operation, but obviously we cannot do this, no? Because unless we are implementing here like a 3-state output, this would be 2 outputs activated at the same time, and I think that would do something not intended. So what would you do to in order to select one of these at different times? Yeah. That's what multiplexer are used to, no? We have a multiplexer here. Let's assume a 4-to-1 multiplexer. So we connect this one to here. We connect this one to here. We have a select. And therefore, at different moments, depending on this select, we can update y with either 1 or if we want to do an operation with that one, we can update the value of y with that new value. And there's still another possibility of just keeping the flip-flop with its current value, no? Because at some points in the circuit, you will have that at any cycle, you need to maintain whatever is in this flip-flop, because this value is being used by another module. So a way of maintaining this value without being updated or set into a constant is by doing this feedback loop, no? So those are the three ways variables may be manipulated. Obviously, you can also have like maybe, for example, if you want to perform division, so you can do this and put this like in another one, no? So whatever is divided by, for example, you want to do this, no? So you would maybe do this again, and again you would be able to modify from where you want to update y. Again, if you use this second one, this will be equal to y equal to y, and this to maintain the value of y. So this is like a basic block we will be using in our designs to represent our variables. I don't know if there's any question with this.
Y for y is just the output from y going back into
It's a feedback loop. Any other question?
How do we choose like select? Do we decide anything for select?
Yeah. We need to have some logic for select. But again, as we were really talking in this section, in our new designs, we have a separate control circuit and a separate data path circuit, no? Which is this one. This is the data path circuit. And we need to design a controller circuit that controls these select signals, because we will have many multiplexers, no? So, but that is like the separation we do in order to facilitate our lives while designing these circuits. Any other question? All right. So, okay, so going back here, well, they're asking us to draw the flow chart of this algorithm. So let's do that. So we can do first, we start, no? Like, that's the beginning, no? Of our flow chart. Then it's telling us that the computation is triggered with a signal go. So nothing happens here until we get this go signal. So if you have ever done a flow chart, you know that conditions are drawn with this diamond. Load 1 to y, 0 to I. Let me just. All right. Yeah, we are going to load 1 to y, 0 to I, and we also need to load the value of x, no? Like, because again, for example, if we have if you remember the past discussion section, well, maybe not exactly that, but if you have an input here, x, you cannot rely on x being forever maintained as the input. You need to put it in a flip-flop so that it stays there, and maybe then I I guess, well, okay, this also operates on over cycles, no? But in order to avoid glitches, you put the value of your input into a flip-flop so as to maintain its value at least for every cycle. So that's why we are also going to load X into one of these registers to be able to maintain the value for all of our circuit. No? And usually, I think what happens is that you load this, and then you can do with X whatever you want, but it's loaded here, and whatever you have as input will not now modify what you have in here. But obviously, you need a little bit more of arrangement here. But there's a step where you load X, and once you load it, the input can be anything, but the X value will be maintained by this separate flip-flop. No, but well, but yeah, here they're telling us that we want a register that holds X. No, so that's why we also need one cycle to load that. So we are loading 3 variables with values. Let's load X, Y equals to 1, I equals to 0. Okay. Then what happens? What happens? We don't need to check these conditions while right now because we already know I is equal to 0. So doesn't matter right now. What we can do is just proceed directly to here and do this operation, no? Which is Y 1/2 of Y plus X over Y. We do this operation. And then we add 1 to I plus plus. Then we check now that the condition is true. If I is less than 128, and it's again a condition. If it's true, then we go back to calculating this. If not, what do? We just okay. So it says that the computation completes by asserting a signal done 1, no? So that's what we are going to do here. Done equal to 1. And then at the end, we'll just make this program cyclical, no? So we're just going to go back to the beginning and wait for the go signal. Because if we don't do this, what happens is that once we go to done, that's it, and our circuit won't respond anymore, no? Like it will only operate one time, and that's it, no? We need to turn off the circuit and turn it on again, no? So doesn't make sense, no? Maybe just make it cyclical. Okay. So this flowchart represents our not only our pseudocode, but the control signals we have here. So is there any question with this? Is this our first step so far? We're trying to I'll say yeah, put in terms of a flowchart this diagram, this algorithm, no? Problem.
Is done equal 1 represent like actually setting the variable or down to 1? Like why does it go over 1?
Oh, because Go depends on the user, but done is something that is activated by the circuit itself. Yeah, well, in here we're assuming that done is equal to 0 everywhere except here. So yeah, I guess yeah, there's some limitations in the way you can express things in here, but yeah, we can just say that it's like this. Because let's see, no? For example, we have again our data path here. We have our controller. And we're having some assumptions here. First of all, we're assuming here comes X. And here comes the go signal. So when we have the go signal, the controller signals the data path to initialize with all these things. Let's assume we have a load signal, maybe. This load signal tells to proceed to do this. And we may have other signals. And in the end, we have this Y will give us Y, and also a done signal that will also be given as input to here. No? And that's the division we are operating on. Although we still need to figure out other controlling signals, but we don't know right now because we haven't designed the circuit. But we will have other controller signals here that control the flow of data in this data panel. But this is not like I guess there's no like law that tells us how to divide controller and data path. This can be done however you like. In here we're doing these assumptions, but maybe you could say that in your design, Y gets put as an input to controller, and control is the one that outputs done. You can do whatever you want, but I guess let's just stick to this design. But yeah, again, these are design choices, but there's no really any rule that tells you. There may be some like empirical rules that facilitate this process, but at the end, it is you, the one who designs, and you should have the judgment to decide how to separate these two parts, no? So yeah, we're doing this like this separation. Now, we would maybe want to, we can either proceed to do the controller part, and the controller part would be a finite state machine, or we can proceed to do the data path, and the data path is the circuit itself. And so I maybe we can do the data path first. Let me think. So let's see, no? Yeah, maybe we can proceed first to do the data path, and then we can figure out which states we can do. Let's see if that works. If not, we can just do first the states and then the data path. So let's see, no? Okay, from the data path, okay, we are already doing this separation. At first, we know that Go, we don't care about Go in the data path because it doesn't deal with that. It only deals with, you could say, this part. This part is of the data path. This part is of the controller only, no? From this separation, we are already doing. So let's see. The first step is that we have two variables, and even then we have to put X in a register, no, to maintain its value. So that's what we are going to draw here. Just okay. So we have X here with a D flip-flop. No, wait, no, this is not a either way. Yeah, no. We have 0, 1. We connect this because the value of X will be loaded here, or the value of X will be maintained. No? Let's put here X in it. This is the initial value of X. And yeah, you could say this is X, no? This multiplexer will be controlled by a signal that let's call it load, no? So this is our signal load. We'll have one of the things they require, no? To maintain X in a register. We're doing that right now. And obviously we can either load a new value or just maintain the state of X there. Then we also have Y and I, which are our two variables. And I'm just going to put two flip-flops here. This will be Y. And we also need a multiplexer No, okay. It should be the other way. Well, okay. So we have the multiplexer, and we need 3 lines right now, or maybe more. And you'll see why. First of all, we have that y is initialized with 1, not at the beginning. So we need to have 1 line for that. Then it can be that y maintains its value. It's gonna be like here. But then y can be updated by the operations we need to do, no? So that's why we have this 3rd line. But we won't connect it right now because we don't know how will we update this y value. And then we have the I value, which is similar to this. So we have this multiplexer. Again, let's put 3 lines. First of all, we can initialize this variable with 0, as it was in our pseudocode. We can keep the value of this variable, or we can modify the value of this variable, no? All right. And yeah, that's our 2 variables, no? Now, and obviously these have some selector lines, no? Let's see. Selector. These are different lines, but first of all, I'm just going to put in selector lines, but these are different. And then we have one magic adder and one magic divider, no? So we're going to put those logic blocks here. We're going to put the divider here, magic divider, which is A over B, and gives us an output. And I'm going to put an addition other here, no? These are our 2 modules that are provided. Okay. So how would you proceed? Well, we already have the logic to do this. Load X, initialize y with 1, initialize I with 0. Now we have to do this. Y plus X over Y multiplied by, well, divided by 2. But there's a problem here, no? Like you could say that each of these blocks operates over 1 cycle. But if you see here, we're doing first a division, then an addition, and then a division. But we only have 1 adder and 1 divider, no? So we cannot really do this in 1 cycle. So that means we need to divide this block into 2. Let's see. We can divide it into y equals to x plus xy. I guess because it only utilizes 1 adder and 1 division. And then we can do x equals to y over 2. So we need to do this again because Jose, we only have 1 divider and 1 adder. This operation needs 2 dividers and 1 adder, so we need to split it somehow. And this is the split we're doing, so that we can, in 1 cycle, utilize the maximum amount of resources, no? Okay, so let's see. Let's first try doing this. So it's x over y. So we have our x here. We connect it here. We have y here. We connect it here. So we have x over y here. And then this plus y. So we will do something like this. This result plus y, no? Here, no? And this result should be equal to y. Well, should be assigned to y. No? All right. But yeah, and it's doing whatever this first operation, no? Okay, we have covered that operation. But then what do we want to reuse that division, no? Because now we want to do y over 2, but these are already connected this way. Well, if you remember the same way we did here, we did multiplexers, no? To allow to reuse these logic blocks. So we are just going to remove these connections, because if we do this, we won't be able to reuse. We need to put the multiplexers. And we're just going to, so basically we know that this A over B will be used 2 times. So we need, and with different inputs. So we need 2 multiplexers here, each for each input. So we have this, here 1, here 1. We connect it to here, to here. We have selectors. And we can at least know right now that X will be connected at first to this one. And we can connect Y to this other one. And this will perform the first operation when we select the correct inputs, X over Y. And then we connect, and we also do the same here, no? We have 2 multiplexers. Because it will be at first whatever we have in this plus y, but then we will also use that other for I plus 1. So we also need 2 multiplexers here. Although in this one we will have 3, because we'll see right now, but just going to put it here like that. So we also have here selector line. And therefore here we remember we're going to connect this one into here, and the Y we're going to connect it to this latter one. So again, now we have and we connect this to here, no? So again, we now modify the circuits to be able to reuse these logic blocks, and it's now letting us do again the first operation in one cycle, and then let's try to do this, which will be y over 2. So let's see, for y over 2 we need this module, and it will be but we need to connect y to this one, no? Because we doing now y over 2, and previously it was x over y, so we need to connect this y in this part, and we need to connect to here, no? So as to now perform y over 2, no? And it's now doing this, and now, well, you can see that this divider is connected directly to here. So just to make it simple to our lives, we can just say, because the result should be instead assigned to y, what we can do this here is just add 0 to this value, and then because this module is connected to y, we don't need to do anything special, no? So that is again to put to remove more, like we could do it, just connect this to here and put another multiplexer, but I guess we can for now, just say that it will still be using the other, but we will add 0, no? But just to make it a little bit simple, so we can put a 0 here, because the other case will be using this other is for I, no? To add 1 to I, no? Which is this case. So we have I here, we haven't done anything with it, but now we are going to connect it to this other part. And we're going to add 1 to it. And this output, we will also connect it to here. So this would be the circuit that allows us to do this. Now there's one thing missing, and it's how do we check this condition, no? How do we check if I is lower than 128? Does anyone have a simple solution to check if I is equal or greater than 128? Based on the bit representation? Yeah.
You can just do a comparative.
But there's even a more simple way, like without using a comparator, or what would you compare more than anything?
Could you also like you want to check if I is less than 130?
You want to check more than anything if it's equal or greater than 128.
You can just you can right shift it. You don't do that. You right shift it 5 times and then see if it's zero or
yeah, but we don't need to do that, no? Because let's see, no? So 128, we have 8 bits. 1, 2, 3, 4, 5, 6, 7. Well, 7. And this bit this is the value of 128, no? If our value is lower than this, then we will have a 0 here, no? If it's greater than that, we will have 128 or greater than that, and that's our condition, no? As you were saying, yeah, we can right shift this value. Well, why not just separate this? These bits are comprised of wires, no? So we can just check this last wire to see if it's a 1, and if it's a 1, that's it, no? So that's as simple as it gets. We just need to check that most significant bit if it's a 0 and 1, and if it's a 1, that's just a signal that connects to our controller, no? So how would we do it here? Well, here we just most significant bit, and this is connected to this our done signal, and it's connected to the controller, no? We don't need to really put any special logic here. We just take the line and connect it to our controller, no? So this will be our circuit for the controller part. I don't know if there's any question with this part. We still need to design the controller part, but at least for the data, we already have these connections, this circuit that let us do what we are supposed to do, no? So any question with this?
Up top in the divider, when you put 2 there, you just meant that you meant 0, 1, 2, right?
Yeah, right now I'm just putting integer values, although you need to understand that this operates over binary values, no? Yeah. Any other question?
What would you put for the selectors in the multiplexers to make sure that they're computing the first one, the first and the next combination?
That's part of the controller, and we still need to design that, no? Because obviously this circuit is missing the control over the selector signals, no? Like if we don't have that control, yeah, we don't know what this circuit is doing, no? Like it can be in a knows what it's doing. That is why we have to create a finite state machine that based on the inputs and well, based on this logic, we are able to control this selector line, no? But we still need to design that. But right now, again, this separation between data path and controller, let us think of these two in separate ways. Well, not as separate because even these two are have some signals that they are shared, no? But again, we have designed this part. We still need to design this part. So is there any questions so far with this part? This part? Because we still need to design this, no? And this is the circuit, no? In fact, let's just numerate these selector lines because these are different. First of all, you can see here that the selector line from here and here are, you could say, would have the same values, no? At different times, because at one time both are 0 and at the other they are both 1, no? So here it doesn't make sense to have separate selector lines. We can just have one, and we can name it selector line 1. Then we can have selector line 2 here, 3. You can have 4 here, and 5. Plus our load signal, no? We will have to control those selector lines. Okay, so we have our data path. So how should we separate this into how to say, into states? Well, this is also like a more or less design choice. I guess the first state is always this one, no? We can separate this as a first state. State 0, no? In this state 0, we wait for the go signal. But again, thinking of each state as a one cycle of our circle, of our clock signal, how many states here extra state do you think here we should use to control this circuit? How many states do you think we should have in order to control these selector lines that allow us to do all these operations? Again, the first one is the initial state where we are waiting for the go signal. So in our let me just, so in abstract like finite state machine, we would be doing this, no? Until another state, no? But what should be that other states? What do you think we should divide it here? Or how many states do you think we can add to this to control this finite state machine?
We do 4 states where you have the start, and you have like initialization where you get the where you set up the values, and then less than 128, and then finish.
So 4 states, do you see?
Yeah.
Yeah, no. Well, here remember that this state, this is a separate state because we cannot proceed from here because we are already using all our resources. So this is a state in itself, because again, we cannot do this operation because we're already using that divider for this operation. So this is a separate state. Then what we could do is, well, the way we have here is that this is another state, and this is a final state. But what I'm thinking is that maybe we could also merge these 2 states. But again, it all depends on, it's a design choice, no? So you can do whatever you want. Just you want to make sure that it's operating correctly. Let's try with this one, and let's check then if it works with other number of states, no? And we can see state 0, state 1, state 2, state 3, and state 4. So the way this would operate is, here we don't care about the changes, no? We're assuming that it stays in this state for 1 cycle. Then it goes to this one, then to this one, and then to this one. And it will go back to state 2. if there's no done signal, either way, it will go to done. It will go to the first state. Maybe we can do something instead like this. But I don't know. I want to check that. Where we would have instead S3. Oh, sorry. Where instead of two separate S3 and S4 states, we will have S3 representing both the original S4 and S3. So I just want to check that, make an experiment. So we have go here, not go. We go here. We go here. If not done here, if done here. So let's check these two ways of doing it. Okay, so this is an abstract view of the finished state machine, but it's not really telling us anything. So we need to create a finished state machine that controls these selector lines. So let's see. For this, we will have then again our states, but in this case, we are going to put all the signals that depend of the controller. So load, select 1, select 2, select 3, select 4, select 5. I'm just going to so each of these states, again, this is like a more detailed view of what's behind these states. And we can put away again our control signals here or transitions here. This is go. This just goes directly here. Goes directly here. Goes directly here. And then goes here if done. And this one goes here. Goes here if not done. So this again is just doing again this. And so there are some like conditions that are implied. Like if you don't put an explicit transition, you could say that it keeps in loop. So we don't really need to specify here that it's being in loop here because we are already putting this transition that depends only on go, but just to make it clear. So now we need to put in each of these what's the value of the control lines, no? So in these states, in the first state, what should be the value of our control signals here? What should we put here? Again, assuming we are waiting for the go signal, we're in this state. So what are the values of our control signals? Okay, we want to control the circuits in order to produce we need to wait for the go signal. So meanwhile, what's the value of this signal, of these control signals? Exactly. We don't care about these ones. because the circuit has not even initiated operation. So it doesn't matter if they are doing anything, we don't care. Like they could be doing addition, division infinitely, we don't care, because we don't have any meaningful values there. State 1 is when we are now performing the loading part, no? So for the loading part, we have to have this in 1. Load should be 1. Load should be 1. And we only care of these 2 lines. We need to make selector line 4 equal to 0 to load this one, and selector line 5 equal to 0 also to load this value, no? So both 4 and 5 are zeros, and the others we don't care because we don't need to use them at that point. So yeah, no, that's our control part. Then we have this operation. So it's x over y and y plus that result. So we would then make sure that x is maintained in its current value. In fact, after its initial loading, we will maintain x in its current value because it will be used in all the other operations, no? So we don't need to change the value anymore. And for state 2, okay, let's see. So first of all, x over y, no? And that is by selector line 1 putting 0 here, no? That's perform the operation. We put a 0 here. Then it's the result of this plus y, no? And this is by choosing 0 in both 2 and 3. And then we're updating the value of y. So we are going to put a 1 in here. And we're going to maintain the value of I, so we put a 2 here. So it's 1 and 2. Okay, so then in this third state, we are doing this y over 2. We're selecting the second line, which is line 1. Here we're just selecting line 0 of selector 2 and selecting line 2 of selector 3. And then we are doing, in here we're updating the value of y, no? So it's again 1 and 2 because we're keeping the value of 5. And here it's what the problem with this design is that we will need to modify our circuit because at this stage it's also using the other. So we will need to put another multiplexer here. So yeah, I don't think we can do this right now. We will need to modify the circuit. So yeah, also based on how you implement your circuit, you may have different possibilities of state machines. But with this design, we cannot do both the I++ and the y over 2 at the same time. Again, because the y over 2 comes to here and is added to 0. But we would need to use also this to add 1 to I, but we cannot do that. So I guess your state machine is also depends on your circuit design. And the last state, so we cannot do this one. And the last state is I++. So this means we maintain the value of y. Well, first of all, we don't care of this because we are not using the divider. And if we have a don't care here, maybe it means no, it doesn't mean anything. Selector 2 should select number 1 because that's the I. Selector 3 should choose also 1. So this is 1, 1. Then selector 4 should be 2 to maintain the value of y. And selector line 5 should be 1, no? And that's it. Again, here we don't need to indicate done equal to 1 because that's already being output by the by just taking the most significant bit of this result, no? So yeah, well, maybe we will need to add a state here that just maintains the value of I, maybe. But for now, I think this is good enough. So yeah, this is obviously we are still just having this finished state representation, maybe a little bit more detailed, but we still need to put all the combinational logic and the flip-flops to maintain the states of this finished state machine, and then connect it to the selector lines. But we are not going to do that because we already have been doing that for too much, no? So is there any question with this? We have now completed the controller part. So now all of our design is complete. Any question with that? This is a little bit more complex, and it involves more of what you have learned throughout this course. So yeah, this design of circuits based on a problem. So no question with this. Because we still have another problem here. So the following is pseudocode for calculating modulo 7 in a binary system. The input, which is 32 bits in size, and output mod are 32-bit integers. The computation is triggered with a signal, go, the same as the previous circuit, for one cycle that allows the input word to register X. And the computation completes by asserting a signal 1 for one cycle. So again, now this is the thing we need to do, check if X is, here we're just going to do this, just to make it more simple right now. Do while. So first we assume X is greater than 7. So we did do this operation to obtain the modulo. So which is a right shift by 3, which in fact is doing X over 8 plus the remainder of the, you could say something like that. The bits that are a bit shifted, which is the 3 bits from here, are added, and then you do this until X is lower or equal to 7. If X is equal to 7, you output 0 into mod. If X is lower than 7, you just take X and put it into mod, no? So we need to do the same things. Here we're just assuming we have a right shift model, and we have a way of separating this line. There's no need of really any special logic to do this, but yeah, no, we also need to perform this comparison. So I'm just going to do it a little fast, just so you can see. Again, flow chart. We know that you start here. We know there's this go signal again. 0 and 1, no? Then we are going to load the value of X, and X, you can see here that it's not only the input but also a variable. We load X, and we also load mod equal to 0. Although we don't need to do exactly that because, well, yeah, let's just load mod with 0 just to initialize the variable. And so we're going to do this operation, which we can do in one cycle because we have 1 bit shifter, and the other again is another. So we have these two, and we can use them parallelly. Then we check if X is greater than 7. X is greater than 7. If yes, we go back to here. If no, we check if X is equal to 7, because that's also determines the value of mod. And here we can have either mod is equal to 0 if this holds true, or mod is equal to X if this holds not true, no? And then it's we have down signal equal to 1, which this to go to, and then we go back to here, no? So is there any question with this diagram? I'm just doing this, but in a flowchart diagram. Again, I'm separating these operations because one thing is to check this, and the other thing is to check this. Any question with this?
If X is 0, or if X is, would not be.
If you can see here, if X is less than 7, mod gets assigned X. In other case, it gets assigned 0, but we already know that whatever goes out from here should be equal or less than 7, no? So that is why we need to check this. And what we can check here is also if X is lower than 7, and just invert the logic is the same, whatever you want to do. But I think it's usually more easy to check if it's equal to a number in circuits. You just need to check, or maybe not. Yeah, who knows? Yeah, well, depends on, yeah, I guess the number. But yeah, let's just do it this way. But yeah, no, this is the flowchart diagram. Now let's see how could we divide this into the controller and data path parts. I'm just going to put it here. So we have data path again, controller, and here comes the go signal. Here comes the X value. And here would output the mod. And in our previous design, Dawn came from here. But now we will change it a little bit just to show you that there's no static way of allocating these signals. Here we will say that Dawn comes from the controller part. Dawn comes from here. And from this controller will be the selector lines, no? We don't know right now which selector lines or we need. And from this data path, because there needs to be a way of signaling the controller that the data path has finished. So we need to send some signal from data path to the controller. And the signal we're going to, I guess, give to our controller will be two signals. It will be, if this is, if this is true, we will create a signal called greater that is equal to X. And we'll create a signal here that is equal when X is equal to 7. And these two signals will be sent to the controller side. And the controller will decide whenever the operation finishes. But again, this is another way of showing you that there's not like a fixed separation maybe of data path and controller signals, at least. And you can also implement in the controller when the operation of the circuit should stop, no? All right. And based on this, the controller will generate the Dawn signal, no? So now our circuit doesn't care about the done signal. We only care about generating in the data path these two signals and the mod, no? So let's see how we should implement the data path side. So we have two variables, which is mod and x. So we proceed to drawing here the flip-flops. Now let me just. So here it's x. Here we draw our multiplexer. As always, this will be having 3 because, again, 1 is for initializing x with whatever the user wants. Then we have a feedback loop to maintain the state of x. And then whatever we update x with, no? And the same with mod, no? We have another flip-flop here. This is mod. Another multiplexer here. 0, 1, 2. 0, no? We'll initialize mod with 0. Feedback loop to maintain states and whatever we want to update mod with. And mod will also be the output of the data path control, the data path part. Okay. So we went until go, but go is part of the controller. We load x and mod 0. And we only need to include here the selector lines. We haven't numbered them. We'll number it. Well, we can number them selector line 1, selector line 2. And then we need to do the whatever operation. No, it's only one operator. No, so operation, no? Right now. So we can do that. We need a bit shifter. You can say it's bit shifter, which is let's do this. We have this bit shifter, which is A, B, and we have this other, which is AB. 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 And we have, so that's addition. And we have this, you can say line splitter. There's no logic needed really, but let's just put something here just to say select 2, no? Basically, you just select you just separate the 3 wires, or you connect 3 wires to the 3 least significant bits and connect it to whatever you want to connect. And so we just connect x to this bit shift. Well, in this case, by 3, no? So it's a constant there. So we connect x to here. Then this will be one of the parts of the addition in here. We split the lines of x in this. And we connect this to a plus b. And whatever we have here, it will update x. All right. And then x. Okay. In the case of mod may have mod is initialized with 0, but mod can also result in 0 if x is equal to 7. Otherwise, it will be assigned to x, no? So from here, we can also now just connect x to here, because we already know that mod can get either 0 or x, no? But we need to define that with the selector lines. And the one that will select which value mod will have is the controller. But to help the controller decide which value, we need to use these 2 signals we have created, where and we need to have some comparators here, no? One will be for a greater comparator, you could say, and one is an equal comparator. And this will be by 7, no? And we will just connect it to X. Let me put this here. To X. And from here, we will get our signals that are connected to the controller, no? Which is greater and equal. And from these signals, we will determine if X has already been, I guess, we have already done all these iterations, no? So this will be the data path part. Again, here we are basically making a different separation between data path and controller. And therefore, the controller part, let's see how many states would we assign. So it will be, again, one state for this part, state 0. Another state for this part to load. Another state, another state for this, yeah. Assign state 2. Another for what? Let me check. Okay. And we need well, this will result automatically in greater or equal. And based on that, we need to if this would be one case, state 3. And this would be the other case, no? This is the state 4. Because again, we need to decide whether to assign one value or the other, and these are two states now because we are doing that based on these signals that are output. And let me just draw the finished state machine. So again, we have 5 states. State S0 with done signal, because the done signal is controlled by the controller. We have the selector line 1 and selector line 2. Only 3 signals. But we have 5 states. All right. Let me just enumerate them correctly. So this is state 1, state 2, state 3, state 4. So the done signal, well, let's see, no? From state 0 to state 1, only if go is 1. If go, else they just go automatically to here. And from state 2, it depends, no? If X is greater than 7, you go to state 3. No, you go to, no, sorry. If equal to 7, you go to state 4. Equal to 7, you go to state 4. You have the equal signal. If you don't have neither the not the equal, not the greater, you go to these states, and these 2 states should go to state 0 again to reinitiate the circuit, no? Automatically. All right, so that's the transition logic. And so yeah, now it's just we know that the down signal should only be 1 whenever we reach any of these, you could say, terminal states. We know that in the first part, we don't care about the selector lines. We know that in the loading part, we need to load 0, 0. No, we need to select 0, 0 lines. We need that in the second state, we need to calculate. So it will be, we need to assign to X. So it will be 1 here. And we need to maintain the value of mod. So 1 and 2. And in the case that we receive, I'll say, in the case where we don't receive any of these signals, or no, we receive these signals, but they are negated. Wait. Okay, yeah. Well, we need to have also. Let me. Okay, there's a thing here. Oh yeah, I think there's a missing thing here. This will keep in here if it's greater, no? So until you don't have a great signal, and if you don't have an equal signal, you will go to the state, and here you will output. You will maintain the value of X, so it will be 1. Well, in these two cases, it will be 1. 1 or 2? And it will be 2, sorry. And the other case, it will be 0 if it's equal to 7, which is this one. Or 1 if its mod is equal to mod is not well, X is not, is X is lower than 7, no? So this will be 1. So this will be our state machine, but I don't know, I guess I went a little bit too fast, but I guess everyone understand more or less what I was doing here? Like, any question with this? It's the same as the previous exercise, just that we have different separation of data path and controller. Any question with this? Because now I just need to tell you something. Yeah, let's just check some things about the timing delays. So propagation delay, you saw it in lecture, no? You have any logic block, no? Propagation delays, time from last input change to last output change. So you have many an input that is many bits in size and an output that is many bits in size also. And at some point you change the input, but there's a time period during which it changes. And based on that, it will change the output, no? So this time between you change the last input bit of the input and the last input bit of the output changes is called the propagation delay. And it's usually what's it? Expressed with this TDAB, A from B, and D, no, which is propagation delay. Contamination delay is the time from first input change, from when you start changing the input until the first output change, when the output starts changing. No? And it's usually expressed with TCAB, from A to B, and C is the contamination. No? So yeah, these are two of important delays. One tells you a little bit about how long do you need to wait, and the other how fast will the input will be propagated to the output. So any question with this? Because we'll be doing some exercises. There's also based on a flip-flop. So the flip-flops update the value based on the edge clock, rising edge of the clock. And in the D flip-flop, it follows the output to what you have in D. But for this to work, you have to maintain the input value for a certain period of time before and after the rising edge clock. The time period before the rising edge clock is called the setup time, TS. And the time after the edge clock, rising edge clock, is called the hold time. If you don't do this, the output, the state won't be updated correctly. Now, the contamination and propagation delay are also here, but now with respect to the clock and the state, no? CQ. So the TDCQ is the propagation delay from the clock to the state, to the output. But there's only, the clock signal is only 1 bit inside, you could say. So both propagation and contamination take as its reference the only change there is. Obviously, for the propagation delay is the output will stop changing until this point, and that is at this point to here is the propagation delay, the point where the rising edge clock changes, and the last time at which you will your output will change. And the contamination delay here from clock to state is the time from which you get the clock signal change until it first starts changing the output, no? So is there any question with this? Okay. Contamination delay is the same thing as minimum delay, because the contamination delay is the minimum amount of time for an input signal to change to an output signal to change. So there's a change in the input and a change in the output. A minimum delay is the minimum amount of time from an input signal change to an output signal taking its correct value. But this doesn't mean the output should change. No, you can change the input. That doesn't mean the output should change, but in the contamination delay, it needs to change. No, so that's the difference, you could say. No, because propagation delay takes the maximum amount of time between a signal change and its output reflection. But here, minimum delay is just you change an input, and it may happen that the output doesn't change, you know. So you only need to consider, well, if it doesn't change, I guess minimum delay is 0, maybe, I don't know. But that's not really used. What is just this contamination delay where you change an input and you see how fast the output reacts. But the output should change, no?
And just like contamination delay isn't always the same as minimum delay, propagation delay isn't always maximum delay, right?
No, in this case, propagation delay is usually maximum delay, because maximum delay only occurs when there's a change in input and output, and you need to wait for that output to change. So in that case, I would say, yeah, propagation delay is usually maximum delay. But it's not the same with contamination delay, again, because you do need to wait for this signal change, no? Okay, so there are some constraints with this setup and hold times. Again, these times you need to wait before and after the clock rising edge in your circuit. So first of all, for the setup time, the time you need to maintain this value in the input of your flip-flop in order for it to so the time before the clock edge signal, so that the flip-flop does accept that value, I guess. And the setup time constraint is related with the maximum, with the greatest delay that there can be in your circuit. And therefore you can see the clock period should be greater or equal than the time period between the delay propagation between the clock to the state of the flip-flops, plus the maximum delay of your combinational logic plus the setup time, no? So let's see. For example, because what could happen? Let's see, no. So we have this clock signal. It updates. We already identify the logic block that has the maximum delay, which is this one. So we're going to test this path because it's the one with the maximum delay. We're going to see if it fulfills the constraint. So first of all, we check the propagation delay, which is the maximum delay between the clock signal to the output of the flip-flop, which is this one, once we get a rising edge of the clock. Then we check this delay of the maximum delay, which is this one, maximum propagation delay of this part. And then if we have some time before the next clock signal, and this time allows us to, and the time period that you need to set up the input in our flip-flop is lower than this, that's good. And we may even have some slack time. And that is good because what happens if we don't have enough time to set up the value here? That means, for example, if we have, for example, 0 here, and we update the clock and it updates the flip-flops, and now there's a 1 here, and from here we should get a 1, but there's still this 0. If the output doesn't arrive in time, this flip-flop will still maintain whatever previous value it had and will propagate it to the other parts of the circuit, but that will be incorrect, no? Because the new value here, A, that should output a 1 here, is not being taken into account, no? So you don't have enough time for the setup time. The flip-flops will not reflect the most recent information. So that is, and you can solve that by slowing down the clock period so that you have more slack time. So that is the setup time. I don't know the constraint for the setup. I don't know if there's any question with this. Because there's some also concern with the hold time. The hold time is that time after you update, well after the clock rising edge, no? When you have also to maintain that value in the flip-flop. And for this, we need to evaluate the shortest path. And we have this constraint that the hold time should be less or equal than the contamination delay between the clock and Q. The time during the clock signal changes and the fastest response of the flip-flop, plus the least the minimum delay of any combinational logic you have. This is the shortest path. And let's check it, no? So in the shortest path, you have this TCQ, the contamination delay, and then you have this minimum, and this should be greater than the hold time, no? And you have here the hold time, because what happens if this is not, the hold time is greater than this delay? That means that the next output of this flip-flop will contaminate the previous value of the flip-flop and will corrupt whatever next value this flip-flop should give, no? Like this will be like would not respect this whole time during which, after the clock edge, during which the flip-flop, the input should be maintaining the flip-flop, and will modify that value, no? Before it needs to be modified. So that is why your hold time should be less than this time, and there should you should also have some slack time, and this cannot be fixed by slowing the clock, because if you slow the clock, you will still have this problem. So what you do is that you usually put some buffers here, like add more gates. Well, buffers just like forward the value you have in the input, but that adds some delay. So you just add many buffers, and that will solve this problem. No? And now let me just do some quick problems with respect to this. So this in this case, they're telling us find the propagation and contamination delay for each input of the following circuit. You will have 4 contamination delays and 4 propagation delays for each of the inputs. Usually you just take the maximum and minimum propagation and contamination delays, but here it's asking us for each of the inputs, no? That can also happen. Assume each gate has a delay of 10 picoseconds. So in here, you can say the propagation and contamination delay for each gate is equal. It's 10 picoseconds. And let's see. Let's check, for example, the propagation delay of TBX, contamination of TBX, and the one from TCDX, no? So this is first the propagation delay from B to X. And this is the greatest, the maximum delay you can have, no? So you will have something like here it will be something like I'll say. Well, first of all, you need to check if whatever you put in B does modify whatever you have in the output. And then operate based on that. Here we're just assuming that that's happening, but yeah, well, I guess let's see. For example, if we have a 0 here, well, yeah, I guess, well, we won't do it right now, but yeah, you just need to check that whatever you put in this input, it will affect the output, no? And yeah, that's one. So we can and that it affects on each of these paths. So let's just do the propagation delay. The propagation delay would be just the longest path. For example, we have that this gate, then you have this gate, then you have this gate, then you have this gate. 4 gates, no? The shortest path is 1, 2, 3. So in the propagation delay, you would check the longest path, which is 4 gates, and each of these gates have delay of 10 picoseconds. So should it be 40 picoseconds? The contamination delay is the shortest path, which is 30 picoseconds, because there's 1, 2, 3, and the other is 1, 2, 3, 4. But again, you need to check that there's really a change of outputs if you change this input in these 2 paths. But I guess right now we're not checking that, but let's assume that happens. For TDDX, let's see, the longest path is 1, 2, 3, 4, 5. So 5 picoseconds. CDX is 1, 2, 3. So this is the contamination delay. I guess any question with this? And just to finish this, we're now doing it with flip-flops. And now the flip-flops do have different contamination and propagation delays. These gates have equal delay of 10 picoseconds. So let's just check TDAX, TCAX, TDBX, and TCBX. So here, propagation, we take this one, 30 plus 1, 2, 3. Yeah, no? 1, 2, 3. Which is 30. So this is 60, no? Then the contamination is 15 plus 1, 2, which is 20. So it's 35. BX, the propagation is 10 plus 1, 2, 3, 30, which is 40. And contamination is 1, 2, 3. So I think it's the same, no? Oh, wait. 1, 2, 3. Yeah. I know, but it's 5, no? Contamination is 5. So yeah, that would be the way of doing it. I don't know, any question with this? Next week we will also be doing some exercises with it, but just to give you an idea of what kind of exercises you'll find. I guess if not, just fill out the form.